I'd like to do a little iPad work here and show what the geometry of eclipses looks like for the sun and moon in our solar system. There were some questions about it. It does get incredibly complicated. So first of all, let's start by drawing a plane. And this is going to be a little bit challenging even for me because normally I do this on a very large whiteboard. But we're going to do our best to do it on an iPad. So let's see what happens. Hopefully my audio will continue to sound pretty good. This is purple plane here is the ecliptic, which is the plane that the Earth and most other planets, I should say, orbit our sun. So here I have just laid out the orbital path of the Earth, and you can imagine that we're looking down from above the North Pole region of the ecliptic, or of the Earth. I know there's no such thing as the north of the ecliptic, but we're doing the best we can with what we got there. And then we're going to draw the circumstance of an eclipse. So I'm going to take another color here, and I'm going to draw another plane. And this plane is going to be interesting because it intersects our ecliptic plane at an angle of about 5 degrees. So I'm going to draw this line, which we'll talk about momentarily, and we're going to draw this plane. So here is another plane. And this plane is intersecting our ecliptic at an angle of 5 degrees. Now this plane that I'm drawing, the dashed line is below the ecliptic and the solid line is above the ecliptic, is the orbital plane of our moon. And so in the center of that, I'll put a red dot, and that is the Earth. So I'll just make a note that a red dot is the planet Earth. The green plane and the green line has to do with the moon's orbit. So let's go back and choose green again and draw the moon's orbit. In fact, I'm going to delete that because there's something interesting about the orbit I want you to see. That here it's above the ecliptic plane, and over here it's below the ecliptic plane. So that's the lunar orbit. And the moon, we're going to make pink. And we're going to put it in a couple of places. We're going to put a pink moon there. I'm going to make sure that we can see this. And I'm also going to put it here, and I'm going to put it here. We're going to label those 1, 2, and 3. The moon orbits, as you know, and the moon's orbit is a 27-day period for a 360-degree orbit, roughly. It's about 29 days from phase like new moon to the next new moon. And that's because we actually are orbiting the sun and the angles have to change. The moon has to orbit just a little bit more in its orbital path in order to come back to the same phase. Very much like a solar day is to a sidereal day for the planet Earth. Now, we're looking at this diagram of 3 possible positions of the moon relative to the purple dot in the center, which is our sun. If the moon is in position 2, there cannot be an eclipse because the moon is not blocking the sun in the sky, nor is the Earth blocking the sun's light from the moon in the sky. So there's neither a solar nor lunar eclipse when the moon is at position 2. But if the moon is at position 1 or 3 on that interesting dashed line, which is the intersection of the 2 planes, and when that intersecting line of the 2 planes aims directly at the sun, then you can have an eclipse. And we're going to give that line a name. We're going to call that the line of nodes. The nodes are where the moon in its orbit rises above our ecliptic plane. We call that the ascending node. And when the moon, and that would be at position 1 actually in this diagram. And when the moon is at 2, it's 5 degrees above the ecliptic from our position here on Earth. When the moon drops back down and hits position 3, That's another node. It's going through the line of nodes, and we call that the descending node of the moon's orbit. And then it continues to go 5 degrees below the ecliptic from our viewpoint here on Earth. So at position 1, you're going to get a lunar eclipse. The moon is on the line of nodes. It's on the other side of the Earth from the sun. So the sun is being blocked by the Earth's shadow. And the line of nodes is aiming directly at the sun. At position 3, you'd see a solar eclipse. And if things were perfectly aligned, namely the moon is on the line of nodes, and the line of nodes is precisely aimed directly at the center of the sun, you could have a total solar eclipse, which is really cool. And if you ever get to see one, I highly recommend it. Now, why does an eclipse not happen all the time? Well, because the moon can be anywhere between positions 1 and 3 and between 3 and 1, while that line of nodes happens to be aiming at the sun. And the line of nodes doesn't always aim at the sun. In fact, the line of nodes is kind of creepy. Let's draw another one of these. We're going to put the Earth over here now. We'll call this position A. And we'll put over here, we'll call this position B. We'll draw the line of nodes. And there we have the line of nodes. Oops. Didn't want to do that. That's better. It's funny how you can delete so much so quickly. So there we go. Now here you see that just about 4 months later, we've orbited around the sun, and the line of nodes is not aiming at the sun at all. And it doesn't matter where the moon is in its orbit. The moon could be in any of those locations. It could be here, it could be here, it could be here, and it could be here. But you'll never get an eclipse, because when it's in line with the sun, it's going to be below it in this case. And when it's on the other side of the Earth from the sun, it's going to be 5 degrees above the ecliptic. So if it's not on the ecliptic, you're not blocking the sun, because the sun is always on the ecliptic, right? So this is kind of cool. Let's just draw an arrow here for the line of nodes. And the line of nodes is also very subtly twisting. It's very subtly twisting. And if you look carefully, the line of nodes at A and the line of nodes at B, they're not parallel. That's because the line of nodes twists clockwise over the course of quite a long time. It's called the Saros cycle. And if you're interested in the Saros cycle, I would recommend investigating that on Wikipedia. The Saros cycle is approximately 18 years and 11 days, if I get that right, or about 223 lunar synodic months. That is phase series, about 233 phase series. So the whole thing rotates all the way around, which is really cool and something that definitely will be a little bit surprising. That is to say that if we continue this motion and just kind of keep orbiting, that means by the time you get to the left-hand side over here, the line of nodes is going to be aiming more like this. It's going to be even more dramatically twisting to the right. And then it'll be aiming over here. Then it'll be aiming over like this. Kind of neat, huh? And so 18 years and 11 days later, it will make a complete 360 rotation, that line of nodes. Isn't that great? And that's why we don't see eclipses as often as we wish. It's not just because of the line of nodes rotating and everything. It's also because the moon has to be precisely placed on the line of nodes, and the line of nodes has to be aiming directly at the sun. I hope that helps.